In 1823, a blacksmith in the English countryside buried a fistful of iron scraps beneath his apple trees. No fertilizer, no compost, no chemicals, just rusted metal from his forge floor. Within 2 seasons, neighbors reported his fruit was larger, deeper in color, and his trees never yellowed the way theirs did. The practice spread across Victorian England. Gardeners, orchardists, and estate groundskeepers swore by it. Then, almost overnight, the advice vanished from every manual, every almanac, every extension bulletin. We have all been told that plants need nitrogen, phosphorus, and potassium. But what if the missing ingredient was already rusting in your garage? The village blacksmith was not a gardener. He was an iron worker. Born into a trade that stretched back thousands of years, the smiths of Georgian and Victorian England sat at the center of rural life. Every town had one. Every farm depended on one. And every smithy produced something that most people threw away without a second thought: slag, scale, filings, broken nails, failed forgings. Iron scraps too small or too warped to sell. Nobody recorded who first noticed what happened when those scraps ended up in the soil. But by the early 1800s, the practice had become common knowledge among English country gardeners. Gertrude Jekyll, one of the most influential garden designers in history, documented the traditions of village blacksmiths in her 1904 book on Old English country life. The forge was the heartbeat of the village, and the waste from the forge had a second life that nobody in the modern fertilizer industry wants to talk about. The logic was simple. Fruit trees near the smithy grew stronger. Rose bushes planted where iron scraps were dumped bloomed with deeper color. Hydrangeas shifted from pink to vivid blue in soil where old horseshoe nails had been buried for years. Victorian estate gardeners began requesting iron waste from local blacksmiths, specifically for their kitchen gardens and orchards. It was not a theory. It was not an experiment. It was 200 years of observation by people who lived and died by what their soil could produce. Then the 20th century arrived, and a new industry needed that knowledge to disappear. The anecdotal evidence is overwhelming, and it stretches across continents. In forums, in old gardening books, in family traditions passed down through generations, the same story repeats. A gardener buries rusty nails around a struggling citrus tree. Within weeks, the yellowing leaves turn green again. A homesteader pushes old iron staples into the soil around a dying lemon tree. It recovers. A family in Wyoming digs up an old garden bed and finds a cast iron pan buried in the soil beneath the most productive hydrangea on the street. Nobody planted it there on purpose, but for decades that bush produced the most vivid blue flowers anyone had ever seen. In Ohio, gardeners had been burying nails beside tomato plants for generations. The tradition is so widespread that agricultural extension offices have had to publish bulletins specifically telling people to stop doing it. Think about that. The practice is so persistent, so deeply embedded in gardening culture, that institutions have had to actively campaign against it. And yet when one Wyoming gardener had her soil tested after years of finding rusty hardware in her beds, the analyst told her the iron was not showing up in the results. The official explanation was simple. That kind of iron does not break down. That kind of iron is unavailable to plants. Case closed. Or is it? Here's what the garden centers tell you. Rust is iron oxide. Iron oxide is insoluble. Plants cannot absorb insoluble compounds. Therefore, rusty nails are useless. End of discussion. But that explanation ignores everything we have learned about soil biology in the last 30 years. And it ignores it deliberately. Iron is the 4th most abundant element in the Earth's crust. It is present in virtually every soil on the planet. And yet iron deficiency, known as chlorosis, is one of the most common nutritional disorders in plants worldwide. Roughly 1/3 of the Earth's agricultural soil is considered iron deficient, not because the iron is absent, but because it is locked up. In alkaline and calcareous soils, which cover 30% of the planet's surface, iron binds to other particles and becomes unavailable to roots. Plants need iron for chlorophyll synthesis. Without iron, leaves turn pale yellow while the veins stay green, creating that sickly web-like pattern that every gardener dreads. Iron is also essential for electron transport during photosynthesis and respiration. It is a cofactor for dozens of enzymes and proteins. Without adequate iron, a plant slowly starves even in nutrient-rich soil. Now here's the part they leave out. Plants do not absorb iron passively. They fight for it. When a plant detects iron deficiency, it activates one of two sophisticated strategies that scientists have documented in extraordinary detail. Strategy 1 plants, which include tomatoes, peppers, and most fruit trees, acidify the soil around their roots by pumping out protons and organic acids. This lowers the pH in the immediate root zone and converts insoluble iron into soluble forms. They also release compounds called reductases that strip electrons from iron 3 and convert it to iron 2. The form roots can actually absorb. But here's the part that blows the whole rusty nail myth wide open. Plants do not do this alone. Their roots are surrounded by billions of soil bacteria and fungi that produce their own iron-chelating compounds called siderophores. These microscopic iron scavengers are so effective that published research has shown they can provide iron to iron-starved tomato plants in hydroponic conditions where no other iron source was available. Pseudomonas bacteria in the root zone produce siderophores that chelate iron 3 and deliver it directly to plant roots. These bacteria can even trigger plants to upregulate their own iron absorption machinery. So when you bury a rusty nail in biologically active soil, you are not just dropping insoluble iron oxide into dirt. You are placing a slow-release iron source into a living ecosystem of bacteria and fungi that have evolved specifically to extract chelate and deliver iron to plant roots. The nail is not the fertilizer. The nail is the fuel for a biological machine that already exists beneath your feet. Then came the debunkers. University Extension Services published articles calling rusty nails a myth. Gardening websites ran headlines declaring the practice useless. Social media filled with confident experts repeating the same line. Iron oxide is insoluble. End of story. The question was never whether the science is nuanced. It was whether the practice could be dismissed in a single sentence, and dismiss it they did. By the early 2000s, the blacksmith tradition had been reduced to an old wives' tale. The question of how soil microbes interact with corroding iron was not explored. It was ignored. The conversation moved on. The shelves stayed full. And those shelves are where the real story begins. The global chelated iron fertilizer market was valued at roughly $2.5 billion in 2023 and is projected to nearly double by the end of the decade. Companies like BASF, Yara International, and Nouryon dominate this space. Nouryon alone paid $320 million to acquire a Polish chelated fertilizer company to expand its product line. Iron chelate fertilizer accounts for nearly half of all chelated micronutrient sales worldwide. These products work by wrapping iron molecules in synthetic chelating agents, chemical cages that keep the iron soluble and available to plant roots regardless of soil pH. They are effective. They are also expensive. A small bag of chelated iron for a home garden costs $10 to $20 and lasts a few weeks. A handful of rusty nails from your garage costs nothing and lasts years. The entire chelated iron industry exists because iron in its natural oxidized state is supposedly unavailable. The entire business model depends on that claim remaining unchallenged. Now ask yourself why no major agricultural institution has funded a serious long-term study on how corroding iron interacts with rhizosphere bacteria in biologically active soil. The mechanism is understood in the microbiology literature. Siderophore production by soil bacteria is one of the most well-documented phenomena in soil science. And yet, no one has connected those dots commercially, because connecting those dots does not sell product. The rusty nail was never debunked by science. It was debunked by marketing. And the line between the two has been blurred so thoroughly that most gardeners cannot tell the difference. In recent years, the research has quietly caught up with what blacksmiths knew 2 centuries ago. Published studies from institutions in Spain, India, and China have demonstrated that siderophore-producing bacteria isolated from iron-deficient soils can rescue chlorotic plants more effectively than some synthetic treatments. In one study, researchers grew iron-starved tomato plants in hydroponic conditions and then introduced bacterial siderophores as the only iron source. The plants recovered. Chlorosis reversed. Green color returned to the leaves. The bacteria had done what the textbooks said was impossible. They chelated insoluble iron and delivered it to roots that were desperate for it. Another line of research showed that plant roots do not just passively wait for iron. When iron deficient, they release phenolic compounds that selectively promote the growth of siderophore-producing bacteria while suppressing other microbes. The plant is actively recruiting its own iron mining crew. It is building a microbial supply chain in real time. The science goes even deeper. Bacillus subtilis, a common soil bacterium, has been shown to trigger plants to upregulate their own iron absorption genes through volatile organic compounds. The bacteria do not even need to touch the roots. They send chemical signals through the soil that tell the plant to prepare for incoming iron. Now place a corroding iron nail into this system. The nail slowly oxidizes, releasing iron oxide particles into the surrounding soil. Bacteria colonize the nail surface. They produce organic acids and siderophores that dissolve the iron and convert it into bioavailable forms. The plant's roots, already primed by bacterial signals, absorb the chelated iron efficiently. One published analysis estimated that a small bare iron nail in warm, moist, biologically active soil can undergo significant degradation within 1 to 5 years, with surface rust appearing within days and bioavailable iron fragments entering the root zone within months. In acidic, organic, rich soils with active microbial communities, the process accelerates dramatically. This is not magic. This is not an old wives' tale. This is soil microbiology operating exactly as it was designed to, with a 200-year-old input that costs absolutely nothing. Not every rusty nail is the same, and not every method carries the same risk. Old-fashioned iron nails, the kind blacksmiths made by hand for centuries, were simple carbon steel. No coatings, no chemicals, no zinc plating. These are exactly the kind of nails that corrode safely in soil and release nothing but iron oxide. Modern nails are different. Galvanized nails are coated in zinc to prevent rusting. Some construction nails carry chemical treatments or cadmium plating that you absolutely do not want near food crops. If you're going to try this, use only uncoated carbon steel nails or old iron hardware that shows natural rust. There is also the obvious safety concern. Buried nails can puncture equipment, injure hands, and cause real harm if forgotten. The safest approach is to use rusty nail water. Submerge a handful of old nails in a bucket of water for 5 to 7 days until the water turns reddish-brown. Use that water to irrigate your plants. You get the iron without the hazard, simple, safe, free. The rusty nail tea method is the simplest way to turn scrap metal into a living iron supplement for your garden. Grab 8 to 10 old uncoated nails or any piece of rusting iron hardware. Drop them into a 5-liter bucket of water. Leave the bucket in a warm spot for 5 to 7 days. When the water turns a reddish-brown color, it is ready. Use this iron water to irrigate your plants once every 2 to 3 weeks. Pour it directly at the base. Do not drench the leaves. The iron-rich water enters the soil where root zone bacteria can immediately begin chelating and processing it. For container plants, push 3 to 4 rusty nails directly into the soil around the edges of the pot. Every time you water, a small amount of iron leaches into the root zone. Acid-loving plants like gardenias, azaleas, ferns, and citrus respond especially well because their preferred low pH environment accelerates iron dissolution. For garden beds, the old blacksmith method still works. Bury a small handful of rusty nails or iron scraps 4 to 6 inches deep around the drip line of fruit trees or beside tomato plants at transplanting time. The key is biologically active soil. If your soil is dead clay with no organic matter, the nails will just sit there. Add compost. Add mulch. Build the microbial population that does the actual work of converting iron oxide into plant food. Track your results. Photograph your plants every 2 weeks. Compare leaf color, growth rate, and fruit production against untreated controls. One gardener documented his tomato plants producing visibly deeper red fruit within a single growing season, using nothing but rusty nail water and compost. Today, the global chelated iron market generates billions, while iron chlorosis remains one of the most common plant disorders on the planet. 30% of agricultural soil locks up iron so tightly that farmers must buy synthetic chelates just to grow a healthy crop. Meanwhile, soil bacteria have been solving this exact problem for billions of years, for free, using nothing but the iron that is already there. A rusty nail will not replace a soil test. It will not cure every deficiency, and it will not outperform a precisely formulated chelated iron application on a commercial farm. But for a home gardener with yellowing leaves and a bucket of old hardware in the garage, it is a 200-year-old experiment that costs nothing and risks nothing. The blacksmiths did not have electron microscopes. They did not know about siderophores or rhizosphere bacteria or strategy 1 iron uptake mechanisms. They just watched what happened when iron met soil, and what they saw was enough. The real question is not whether rusty nails help plants grow. The real question is why a $2.5 billion industry needs you to believe they do not. If this vault opens something for you, subscribe and hit the bell. Every like and share helps preserve this knowledge. The next vault opens soon.